In this video capsule, we shall look at the waveforms, some critical waveforms of the forward converter. The output portion of the forward converter is like the buck converter, and therefore the inductor current, the capacitor current, and the output load current parts of the waveforms will be exactly same as that of the equivalent buck converter waveforms that we discussed. What we should now look at is the waveforms of the primary side switch, the secondary side currents, and the freewheeling currents for core resetting. These are critical waveforms which we will look at, and that will give us an idea of how to go about rating the devices and selecting the components.
So you see here that the forward converter is moved to one corner, so that I have made some space here to put in the waveforms. Like before, when we were discussing the buck converter, I have here the waveform of VG. Now VG is actually the gate waveform or the base drive waveform that you would give here. So this is the signal that you would give here. When the signal is high, this BJT or the power semiconductor switch will turn on. So this is the period when the switch is on, this is the period when switch is off. This is the DTS period, on time, 1 minus DTS period, off time. Now let us look at some critical waveforms. We know how the buck converter operates, and we know how the pole voltage will be. Exactly like what we discussed for the buck converter. One difference would be the turns ratio N coming into the picture. I will briefly show you that, and then we can move on to other waveforms. Now let us say I will position VP here. The waveform would look something like this, just like before. The only difference would be in the value here, which is NV in. When the switch is on, during that time here you have V in, and what gets transferred to the secondary is N times V in, and N times V in will come across at this point. So that is what we have shown here. And during the time when the switch is off, the inductor current is freewheeling in this fashion, and VP is 0. So that is what you would get here, and the resulting average of that would be the V0. So let us say I will position the average somewhere here, just an indicative measure, and V0 is something like this. So this is the V0 waveform. So as far as the buck converter operation is concerned, it is the buck portion, that is the L and C, it is exactly same as before. The inductor current operation is also very similar. We will revisit that later on, but there are some few other important waveforms that you need to look at. The primary current that is flowing through the switch, and the portion of the current that is freewheeling when the switch is off. This is actually the core reset current, the current that will reset the flux within the core and makes it ready for operation in the next switching cycle. Now let me draw the magnetizing part for IM that is flowing through the primary of the transformer. So when the switch is on, there is a voltage V in applied across the primary, which is a constant voltage. So therefore the magnetizing part will rise up linearly. The reason is that voltage of the primary is equal to L magnetizing dim by dt. So as V primary is nothing but V in, which is equal to Lm dim by dt. Dim by dt is equal to V in by Lm, the rate is constant. And therefore the magnetizing current rises up linearly like this. So everywhere you will see during the time when it is on, it should go like this. But that once it has gone, the magnetizing current has gone up like that. You should also note that by the Faraday's law, there is another fundamental relationship, which is N primary d phi by dt, the flux within the core, which is a more primary relationship. So this d phi by dt within the core is also having a similar form like the LDIM by dt, and therefore phi also would increase within the core linearly. So this is increasing V in by NP primary, and this is increasing V in by Lm. So the slope is like that. Now after having reached the maximum, now you have switched off the device. Once you have switched off the device, you see that the current through the transformer is immediately switched off. This will go down to, is supposed to go down to 0, which is a high di by dt, negative di by dt. Very narrow time, and then you are cutting off the current, that is a di by dt, and therefore a negative di by dt means that the voltage induced here will change polarity. So this will become positive and that will become negative. The dot end will become negative, this non-dot end will become positive, and this will drive a current through this closed circuit path, turning on this diode. So once it drives the current, this is acting now like a generator. L by R time constant, it will fall exponentially. So the current, the magnetizing current, will start falling exponentially like this. With the time constant, if this is R and Lm is the magnetizing, this will have a time constant tau is equal to Lm by R, L by R. Now the flux also follows, looking at this Faraday's equation, the flux will follow the magnetizing current. So therefore the flux shape also will be similar to the flux, the current shape. So this will also go in this way, and this is called resetting the core. So bringing it back to 0, that phenomena is called core resetting, and it is very essential for proper operation of transformers. Core resetting has to be done whichever be the topology. So once the core is reset at this point here, again it is ready to begin its journey in the next cycle. So this is how the magnetizing part freewheels through this freewheeling circuit. So what is the current through the switch IQ? Now let me draw the current through IQ. It has, as I said, two parts, the magnetizing part and a load reflected part. So let me draw also the load reflected part and show you how the primary switch current looks like. So the magnetizing current in the primary we saw was like this. It had a linear part, exponential decay, linear part, exponential decay, so on and so forth, keeps going like that. So this is IM, the magnetizing part. Now we saw the current here. This was the inductor current, that portion of the inductor current which is flowing through here, and it had a waveform which is like this. So this is the reflected part of the secondary current. Now you see that in the secondary, the inductor current average was I naught, and therefore this value would have been I naught. But recall that when you take it to the primary side, it becomes N I naught. So this value, very important, gets scaled by N. Now the load reflected part plus the part magnetizing part is the current that will flow through the switch. So I will draw the load reflected part like this. This is the load reflected part, and to that let us add the switch part, that is this one. So it gets added like that. So this would be your switch current. So this current is IQ, which is flowing through the switch Q here. So this part, this hashed green part, is flowing, freewheeling through here. I will call it as ID. This is ID. And the magnetizing part is the one which is actually included in the IQ part itself. So this is how the current waveforms flow in the primary and the secondary of the forward converter. We will just have a look at the voltage waveforms too, to understand what is happening to the voltage ratings of the converter. Consider the switch Q, and let us look at the voltage waveform across the switch here, VQ. Now VQ, when it is on, it is just the on state drop. So all these would be on state drops. When the switch is off, you see that there is a freewheeling current flowing through in this fashion. There is a drop here. There will of course be the diode drop, and then Vin, which completes the circuit here like this. So if you look at the Kirchhoff's loop along this path, the Kirchhoff's loop, you will see the voltage that you see across this when this is off is this R drop, diode drop, and the Vin value there. So what actually will be VQ during the off state would be Vin plus IR drop, whatever is the current I that flows through here, and let's say this is R, plus VD, or the diode on state drop. So that is what will come here. And out of this, you will see that this is a varying quantity, and we saw that the current here, the magnetizing current, is going down exponentially. R being constant, IR drop will also have this shape. And ultimately it should, when it goes to 0, it should settle to V in. So if this is the V in value, you will see that the voltage will start moving in this fashion. The voltage across the device, the switch, will be like this. So now if you look at the rating for this Q, the voltage rating should be such that the off-state voltage withstanding capability should be such that it is greater than this quantity. And what is that I? I in general has to be the magnetizing current, but however you will see in practice there is a leakage component here. There will be a leakage current, a leakage, primary leakage in the transformer series with it. So during the time when the transistor was on, this leakage was carrying both the magnetizing plus the load reflected component. So N I naught component. So N I naught plus Im value will be the value which I will start off at this point, at this. And then once the leakage energy has decayed, then the magnetizing energy will decay and form, take this wave shape. So during the instant of switch off, you may see in the scope a very high spike like this. Now that is due to the leakage, and that is when the leakage energy causes that kick. So I will actually be N I naught plus I magnetizing peak. I magnetizing peak. So this into R Vn plus Vd should be less than VCEO rating of the transistor or the MOSFET. So based on this, you know this by design, this by design, this by design, this can be the value, datasheet value chosen from the of the chosen device. Knowing all this, this can be estimated. This is one condition. It only says that the value of R so chosen should meet this constraint. There is another constraint. The value of the R should not be too low to avoid the spike, because if it is too low, there is a time constant involved for this decay, and 5 times the time constant should reset the core flux in the available time T off. So 5 times Lm by R time constant should be less than the T off time, which is 1 minus d Ts time. So this is known, Lm is known from design of the transformer. This value can be estimated. So these two values from these two inequalities will give you a higher range and lower range, and based on these two higher range and lower range, you should pick a value in between this range to satisfy your circuit requirements. Another aspect is that the power dissipation in R, the energy which is stored in the magnetizing inductance is half Lm Imax square. Now this energy has to be dissipated within R every cycle. So into Ts, this is the energy in joules by Ts. Every cycle this energy has to be dissipated, will give you the power dissipation in R, which is half Lm Imag I max square into Fs. Notice that the power dissipation in R is independent of the value of R. So whatever may be the value of R, the power dissipation is fixed. The value of R does two components. One is limit the value of the spike voltage here at VQ spike voltage at the switch off time, and also determines the time constant tau of the decay of the flux. So these two are going to decide the value of R, and the power dissipation is determined only by frequency and the inductance, the magnetizing current components. So this way you can rate the resistance value R. So the switch, both the current and the voltage ratings are known. The voltage rating is basically V in plus IR drop here, and the current rating is whatever value of the current that flows here, peak value, which is I naught, transferred here N I naught plus delta IL. So N times I naught plus delta IL will flow here, load reflected plus I magnetizing. These are the two components that flows through here, and the current has to be accordingly rated. And the diode current here and the diode current here will be rated exactly the same way as we discussed for the buck converter circuit. L and C will be designed in exactly the same way as we did for the buck converter circuit, because the out portion of the circuit is nothing but the buck converter. So we know how to rate the resistor, we know how to rate this transistor switch. The diode here will have a current rating of the magnetizing current average, and a voltage rating. It should withstand V in when the transistor here is switched on. So this way you can rate the various components. It is now a good time for you to simulate the circuit and learn more about the various waveforms at various points and get more insights into this circuit.